Welcome back to another explainer. Today, we're diving headfirst into the high-stakes, sub-zero world of marine refrigeration. We are going to explore exactly how engineers pull off the ultimate balancing act, keeping both the crew and the cargo cool in the middle of the harshest oceans on Earth. Right, let's hook right into why this matters so intensely. Picture this, a single refrigerated container, a reefer, packed wall-to-wall with bananas. That single box can be worth tens of thousands of dollars. And every single piece of that fruit depends entirely on a temperature band held remarkably steady at minus 18 degrees Celsius, sometimes for up to 3 weeks at sea.
Thermodynamics can honestly feel a bit abstract, so here is our roadmap for how we'll break this down. We're looking at the stakes of marine cooling, the vapor compression cycle, scaling up with secondary refrigerants, controlled atmosphere cargo holds, and finally, troubleshooting and air conditioning.
Let's start with Section 1, the stakes of marine cooling. You see, a failure out here isn't just a spoiled lunch in the galley fridge, it's an absolute multi-million-dollar disaster for global trade. If the machinery stops or honestly even fluctuates beyond a couple of degrees, entire shipments are completely ruined. The stakes literally could not be higher for the engineers monitoring these systems. The crucial thing to wrap your head around here is that we aren't actually making things cold. We're actively forcing heat to move against its own natural physics. Heat naturally wants to flow downhill, right? From a hot space to a cold space. While refrigeration uses mechanical work to force that heat to flow uphill. We are literally scooping heat out of the cargo hold and dumping it into the sea or the outside air. So, how do we actually pull off this uphill movement of heat? That brings us to Section 2. The vapor compression cycle. The core physics at play here are just fascinating. Here's what most people miss. The cold we generate doesn't come from some magical freezing machine. It comes from a sudden pressure drop. If you've ever held an aerosol can while spraying it, you know it turns freezing cold in your hand as the gas rapidly expands and depressurizes. That is pure physics, and it's the exact same principle that powers massive shipboard cooling. Let's follow a single drop of refrigerant as it travels through the 4 stages of this cycle. First, the compressor squeezes the gas, raising its pressure and making it very hot. Second, it flows to the condenser, where seawater or air cools it down while it's still under pressure, condensing it into a liquid and rejecting that heat outside. Third, it hits the expansion valve. This is our aerosol can moment. The liquid passes through a tiny valve, the pressure drops suddenly, and it becomes freezing cold. Finally, step 4, it enters the evaporator in the cargo hold. Here, it absorbs the heat from the space, boils back into a vapor, and returns to the compressor to do it all over again. Once you understand that basic 4-step cycle, you face a whole new engineering challenge. And that brings us to Section 3, scaling up secondary refrigerants. Think about it. Primary refrigerants, the chemicals doing the actual phase changing, can be highly risky if they leak. Ammonia, for example, is incredibly efficient, but it's highly toxic and flammable in concentration. It requires extreme leak detection and rigorous emergency response protocols. You absolutely do not want thousands of feet of pipe carrying those kinds of chemicals all over a massive vessel. So engineers restrict the primary refrigerant to one central chiller unit. This unit cools down a completely safe secondary refrigerant, usually a calcium fluoride brine. This safe cold brine is then pumped all over the ship to the various remote cargo holds. It's just a genius way to maintain safety while distributing cooling across a giant ship.
But what if I told you that just making things cold isn't always enough to save the cargo? Welcome to Section 4, Controlled Atmosphere Cargo Holds.
This is where things get truly wild. Controlled atmosphere, or CA technology, actively changes the very air the cargo breathes. Think of it like sealing a piece of fruit in a jar. By lowering the oxygen dramatically, usually down to between 1 and 1.5%, and raising the carbon dioxide up to 25%, we literally starve the fruit of the oxygen it uses to ripen. We slow its respiration rate right down. This buys us extra weeks of shelf life without needing extra cold. Though keep in mind, because this atmosphere won't support human life, it requires incredibly strict safety protocols and complete aeration before any crew member can safely enter the hold.
Actually, I want to bust a massive myth right here. You might logically think, well, if cold is good, colder must be better. Absolutely not. As a rule of thumb, every single degree below the specific commodity's recommended safe range doesn't help. It actually destroys the cargo through what's known as chill damage. Precision is everything. It is definitely not just about blasting the cargo with the coldest air possible. Finally, let's bring this all back to the human element. Moving on to Section 5, troubleshooting and air conditioning. The crew needs to be comfortable regardless of whether the ship is sitting at the equator or navigating the Arctic. To manage this, ships use three main HVAC configurations. The single-duct system is super common on cargo ships, delivering treated air where local vents just adjust the volume. The twin-duct system runs both a hot and a cold duct, mixing them at the cabin. You'll see this a lot on passenger ships where individual comfort is at a premium. And finally, the single duct with reheat is used in cool climates, providing treated air that gets a localized heat boost right at the room thermostat. Ultimately, it's all about managing both temperature and relative humidity. All right, let's test your new knowledge with a real-world detective puzzle. This is something marine engineers face all the time, and it's a great way to see how these systems actually behave. Imagine you're in the control room. You notice a reefer container's compressor is running constantly. It's never shutting off, but the temperature inside the box just won't drop down to its set point. Assuming the door is sealed tight, what system fault would you suspect first? Did you guess a leak? Because that's exactly it. This is a classic symptom-to-cause pattern. If there's a low refrigerant charge, meaning a slow leak has let some of the gas escape, there simply isn't enough fluid circulating in the system. Because of this, the evaporator physically cannot absorb enough heat per cycle. The compressor just runs continuously, desperately chasing a temperature set point it physically cannot reach. But hey, finding leaks isn't just about protecting the cargo. It's about protecting the planet. International regulations are driving a massive shift here. In the past, we used CFCs like R12, but the Montreal Protocol phased those out because they destroyed the ozone layer. Present day, we use HFCs like R134A. They don't deplete the ozone, but they are potent greenhouse gases. So, looking ahead, the future of marine refrigeration, which is heavily regulated by MARPOL, is moving toward natural options like ammonia and CO2. These have zero ozone depletion and very low global warming potential. Which leaves us with a totally fascinating challenge for the future of global logistics. A large container ship might carry well over 1,000 reefer plugs, creating one of the absolute largest electrical loads on any modern vessel. That is a massive continuous power demand that ties directly into the electrical generation topics we'll be covering in episode 6.2. So how will we continue to protect our cargo and comfort our crews, powering this massive uphill movement of heat while simultaneously protecting the atmosphere with new, stricter refrigerants? It's an incredible balancing act of thermodynamics, environmental science, and sheer mechanical power. Thank you so much for joining me on this explainer, and I hope this leaves you looking at the cold sections of the grocery store in a whole new light. Catch you next time.